So we all know that scientific microscopes have become indispensable workhorses of laboratories across the world. They're used in applications ranging from single molecule localization microscopy, where one can observe molecular processes beyond the diffraction limit at tens of nanometers, to image cells and tissues that are hundreds of microns thick. But a common theme amongst microscopes is that the objectives they use have been designed to have the best performance at focus. This makes them inherently 2D. One common method of getting 3D information is axial scanning, but that can be impractical for single molecule imaging or tracking. And also when practical, the limited depth of field of 2D microscopes require finer axial scanning steps to making the process extremely slow. To better understand the limitations of a standard microscope, let's consider an example of three molecules at three different depths. The molecule on the pink plane is in focus, whereas the ones on the green and blue planes are above and below the focal region. When imaged with the standard microscope, the blurring of the airy disk with axial defocus significantly reduces the signal-to-noise ratio of these molecules. Furthermore, the symmetric blurring around the focal position leads to ambiguity in the sign of the axial position. Lastly, the image of all molecules within the depth of focus of the objective look equally sharp, leading to further errors in their axial position determination. However, when we add our phase mask to the imaging system, it modifies its point spread function to overcome these limitations. As an example, when we add a double helix phase mask, you can see that the image of molecules on all the three planes look like two lobes, such that the angle between the two lobes is a function of their axial position. Furthermore, the rotation angle of the molecules above and below focus are distinct, and the rotation continues at a similar rate through the depth of focus region, removing all the ambiguities associated with the airy disk PSF. Here is another view of looking at the same example. On the left, we have the standard microscope, in the middle, the double helix PSF, and on the right, astigmatic. And this is what the image of the molecule would look like as it moves in and out of focus. And in this example, it's easy to see how long the double helix PSF stays in focus compared to standard and the astigmatic PSF. The double helix PSF is one example of engineered PSF that we offer. We have a broad range of phase masks that can give you from about 2x to 30x increase in the depth of field as compared to a standard airy disk system. We also offer multicolor phase masks that exhibit two different PSFs based on the emission color of the molecule, allowing one to simultaneously image two different fluorophores. In order to allow easy access to a library of phase masks, we have developed our spindle family of products, specifically the spindle and the spindle squared. These modules can easily be attached to most scientific microscopes and cameras using standard C-mounts and allow for easy swapping of the phase masks to match the application and microscope setup. Removing the phase mask returns the microscope to its standard bypass mode, so it can be used in its conventional 2D operation. The spindle is a one-channel solution, which can be used for multicolor imaging by either using our multicolor phase masks or imaging the two colors sequentially. The spindle square, on the other hand, is a two-channel solution, where the light from the microscope can be split either by using a dichroic mirror or a polarizing or a non-polarizing beam splitter. Each channel can then be independently modified using a combination of phase masks from a library. The two channels are then combined back onto a single camera to take advantage of large chip sizes available on scientific cameras today. The spindle square allows for easy simultaneous multicolor and multimodal imaging. The data obtained using our phase masks and the spindle module can then be processed using a 3D track software. The software has been developed as an ImageJ plugin to shorten the learning curve for most of our life sciences customers. The software also allows for calibration of the chosen PSF as a function of X, Y, and Z location of an emitter. The localization data can then be processed either using our sparse or overlapping emitter algorithms. Once processed, the results can be filtered using various ROIs and visualized either as depth encoded color maps or TIFF stacks to be used for further processing. The software also includes modules for drift correction and particle tracking. Our solution is enabling new discoveries around the world in life sciences and beyond. and all publications are available on our website. Next, Dr. Dominik Wöll will talk about his experience using the Double Helix PSF and the spindle module for use in studying structures of microgels. With that, take away, Dominik.
Yeah, great. Thank you very much, Novak. Thank you very much, also Ronald, for the introduction before. And I will, of course, also share my screen. Anurag already gave you a nice introduction about the double helix. I will come back to this a bit later, but I actually want to start not with the technique, but with the systems which we apply these to. And actually, let's say my specialty is to do single molecule spectroscopy and microscopy and also super resolution in polymer systems. And for this, so to say, we are the explorers of this polymer galaxy. And of course, unlike for normal galaxies where you use telescopes, of course, we use our nice microscopes, including, of course, the spindle from Double Helix. Yeah, and more particular, we focused in the last year on microgels, or you might also call them nanogels. It depends a bit on the community which you're in. So microgels are basically gel particles. So they are little gels in particular form, and typically most of the time they are actually below a micrometer, so they're in the sub-micrometer range. What is also interesting is these particles, these gel particles. I mean, the density of the gel is not uniform, but it is rather here that you have denser regions in the middle, and outside it gets more sparse. And this is then the profile which we have. And actually, it's not only me who does research on microgels here in Aachen University. It's actually several groups, about 15 to 20 PIs in a big collaborative research center, the so-called SFB 985, which is all about microgels. Yeah. And as I already told you, these microgels have typically diameters beyond 1 micrometer. And of course, this immediately tells a spectroscopist and microscopist that is something for super resolution imaging. So before I go to this, I also want to briefly outline the advantages or the fantastic possibilities we have with microgels. Actually, what you can do, for example, you can functionalize these microgels differently. So for example, you can make compartments in the center, other compartments in the shell, and then functionalize them with different groups, for example, giving rise to tandem catalysis reactions and so on. So you have actually functions in close proximity, which in solution might even cancel out each other. And this gives very interesting possibilities. This is only one of the possibilities. In general, I mean, we can use microgels as building blocks, scavengers and protectors, surfactants, actuators, and ion clouds. And the application from all these properties are in catalysis, uptake and release, so drug delivery, as sensors, also in extraction processes, and also, for example, as responsive membranes. So there are plenty of applications for these microgels, but of course the applications depend on how well we know these systems, and this is why we want to look in detail into them. Yeah, and of course, as I told you, super resolution fluorescence microscopy is a very good tool to investigate them. Now, if you have here different people, you might see different distinctions of all these super resolution methods. I normally like to categorize them in 3, so to say, columns. One are the localization-based methods, the scanning methods, and then we have the structured illumination. And also in this column for me is the image correlation, which I will come back in the end. However, most of this talk and also of our research is based on the localization-based methods. The typical synonyms for them are PALM, STORM, D-STORM, and so on. And what is the key thing here? So we have a single dye molecule, which is a label, for example, for something we want to see. The molecule is 1 nanometer typically in size. This is not the size as you see it, but you see it as a diffraction limited spot of about half of the wavelength. So let's say normally something like 200 to 300 nanometer in diameter. This is not a problem at all, because if you have a single molecule, you know exactly where this is positioned. But if you have, for example, here polymer structure, and you label your polymer structure, all you see when you have now the diffraction limited spots is this. And this is of course not good. And therefore there are methods to circumvent the diffraction limit made of course by very sophisticated people. 3 of them won Nobel Prizes, but there were many others of course also involved. Yeah, so what do we do here? You can do the following. You have here your diffraction limited image, and you do not see the single labels. You also cannot count them basically. So what you do now in this localization-based super resolution methods is you switch off most of the fluorophores, and you have statistically only on 1 per time, or less than 1 per time. And of 1, you can localize very well the center. You do this at different times with others. And so using quite some time, let's say, in the end, you get here, you put together your centers of your signals. And this gives you the super solution, which was also up here, just made by PowerPoint. Up here, you could not resolve them. Down here, you can resolve them. Yeah, in reality, this looks as follows. So this is typical movies of blinking, in this case, Alexa 647 molecules with the right blinking buffer. And actually what we see here is actually really microgels, so signals in microgels. Here's then our typical localization algorithm. These crosses just give you the centers of the spots, and the centers of the spots are just then composed together in this image. And if you do this long enough, you start to see the shape of the microgels. As I told you, they're here approximately 300 to 400 nanometers in diameter. Yeah, this all is fine. We have done quite some research with this, but in the end, microgels are 3-dimensional objects, and of course, it is very important to see also the 3rd dimension. And with the 3rd dimension, I decided to put in 2 slides, which I normally never present, yeah, because actually they are old. They are from 2013, when a PhD student, actually, Oleksiy Nevsky, did a lot of research and tries on getting this 3rd dimension with the point spread function engineering. And we use these methods, which are published here in some of these papers. Yeah, so actually, we used a spatial light modulator. And we had also fantastic help of Alexander Jesacher at the University of Innsbruck. Let's say it took us a lot of time to implement all this. In the end, we managed, and we could program our spatial light modulator to give astigmatism, double helix. We also tried the corkscrew point spread function. This all worked out fantastically for beads, which are rather bright for single molecules. You see here the signal to noise ratio is, let's say, not the most optimal thing. And why I show you this is the following. First of all, I must say it took us really time to get this all working. And in the end, it was not all the optimized, because we had to fight a lot with aberrations. This was the time when I learned what aberrations are and that they can be really nasty. And secondly, with these classical reflective spatial light modulators, we always had to give away 50% of our light due to polarization reasons. Therefore, we were very happy when Double Helix actually came up with these phase masks, which are transmissive and where we don't lose now this 50%. And to have twice as much light, believe me, with single molecules makes a nice difference. Yeah. So, yeah, coming back also just to some, to see just our signals, which we have now and which we can analyze now also rather nicely. Yeah, and when we do super resolution imaging now in microgels with this double helix point spread function, of course, now you don't see the blinking of 1 point, you see the blinking of these 2 loops. And of course, the angle determines the set position of the emitters. Now, of course, it doesn't give you so much if I just show you the 2D picture. Therefore, we go to 3D. And I will show you what we see with all this. We still have the microgels. They are still 400 nanometer approximately in diameter. But the nice thing, what we see, you see even that they are flattened here. And why are they flattened there? They are flattened because they lay on a surface. And this flattens them. And this is actually something which we can see now very nicely. As I will show you in a moment, that gives rise to a very nice, interesting research topic, which we're at the moment exploiting. Yeah, just generally, what do we do now with these 3D super resolution measurements? We can investigate compartmentalization with functional groups in the microgels. We can look at cross-linking densities because we have crosslinks which are actually photo switches, so they can be used for super resolution. We can look at microgel shapes and deformations at interfaces. This I will show you in a moment more. And also what we did is we investigated the local polarity inside microgels. This we did with solvatochromic dyes, specifically with NIRAD here. Yeah, coming to this microgel shape and deformation at interfaces. I mean, we were actually first, I mean, we wanted to do super resolution with these microgels, and to do super resolution, you have to have them immobile for some time. And on the other hand, you do not want to immobilize them in a way that they really do not show the properties which they have in solution. So therefore, we are investigating ways how to immobilize them, but still have them in the spherical original shape as they are in solution. And actually all this then went to a new topic, which was simply investigating the interactions of microgels at different surfaces, which itself is interesting, for example, for sensor applications and so on. And that just to make this story not so long, we investigated different surface modifications, polyethylene glycol, a hydrophilic surface, a hydrophobic carbohydronized surface, and a fluorinated surface. And we actually, in cooperation with Igor Potemkin, that is someone who does simulations on these things, he showed how the shape depends on the surface where you put the microgels, and actually with the 3D super resolution imaging, in this case also using the spindle approach, I mean the double Higgs point spread function, you can see here actually in this data that actually what we see is quite well in agreement with what has been simulated. So I mean we can describe the system quite well. Furthermore, yeah, I also actually, this is also a slide I normally don't present. Here I just want to show you how the data look. Yeah, I mean, often you see the 3D images, but you don't see the data. And I think it's very important also to show the real data. So this is for our different surfaces, how our single molecule emitters look in the different microgels, which you do not see here, of course, yeah, the microgels. Good, yeah, we investigated different surfaces, and also actually we changed the way how we added the microgels to these surfaces, and all this gave them a matrix of investigations. And this all, I don't want to go into detail into this, but it should show you that we can now really see different shapes on different surfaces with different preparation methods. And this is something which is otherwise really hard, or would be almost impossible to do with other methods. Yeah, I mean, because you cannot use really in situ electron microscopy for this. AFM, I mean, of course, gives you the surface, but not really the inside. So, I mean, this is really a very nice method to do this. Yeah. So, with this, I also want to make very briefly some advertising for our own software, so to say. So this would be actually something which comes after all the analysis done, for example, with these 3D tracks. Because actually we were always a bit annoyed with ways how to present our data. And then some people of my group, let's say, just decided, let's not be annoyed, just make our own program. And this is called Microberry. You can access this here on this page here. And it just gives you the options of, for example, going from high to low density regions to make cutting walks, as we call them, to rotate the things, to make walking slices. I'm aware that other programs do this also, but I think we have a lot of options, and also the visualization here is very, I think, very aesthetic. Good. So in my last part, I come now to this last block of methods, actually, and especially here, the image correlation methods. And specifically here, I want to talk about SOPHY. SOPHY is, I think, not as known as the localization-based techniques, but SOPHY can be very strong. And actually, I think it came from the lab of Jörg Enderlein. And we also cooperated with him, and we did some quite interesting things with SOPHY. Actually, what we did is we used one of our preferred photo switches, styrene dyes, which are fluorescent, and which we can use for different methods. Actually, some of them also can be used with the 3D double helix. This is now the thing. So we did this on a spinning disk confocal microscope, but you could also do this on a wide field microscope. And what you use here now is you just switch on and off these molecules, let's say independently of each other, but you do not see the single molecules. So if you do a measurement, actually, it looks like this. You have your structure, your diffraction limited structure, and the structure looks just a bit like blinky, a bit strange, but this is because the single molecules go on and off. And of course, the pixels which have signal intensity in one chromophore, they go on and off in a correlative way, so to say. And by investigating these image correlations, you can actually get a super resolved image. With second order SOPHY, you gain a resolution of 2. With third order SOPHY, a resolution of 3. So the resolution gain is not as high as with localization-based methods, but it is quite also strong. So we could also show that we can separate here. This is polymer micelles, which we could separate here. And now you can say, well, I mean, but a resolution gain of 1, what does it give me? I will tell you one thing which is really strong in SOPHY, because actually you can get a resolution gain of factor of 2 in incredible fast time. As you might know, in these methods, localization-based methods like Palm, you have to measure quite some time, minutes, to get good resolution. With SOPHY, actually, we just measured 200 frames. That was clearly, this was basically seconds. And we got already a resolution which was reasonably better than the diffraction limit. So actually what you can do here, you can play time against temporal against spatial resolution. If you don't need the full spatial resolution, but you need more temporal resolution, you can just play with these factors by choosing the right technique and the right conditions. Okay, why do I tell you this with SOPHY? To come back now to the double helix. Actually, it was an independent idea of 2 researchers which I talked to, and one day, Jörg Enderlein and Peter de Decker. Actually, in the end, we decided to join up and just publish this idea together because they saw that the double helix is a very interesting object, so to say, to do this image correlation. And I show you this here now in this slide, because let's say if you move your image by a certain distance and you do this in the right direction, you hit with the loop of your image, so to say, the other loop of the shifted image. So that means you get a correlation when you do a shift in this direction. And this correlation then gives you some information about the set position of your emitter. And doing this in this first, let's say, brief communication, we just showed here that this is principally possible, and you basically get also a set resolution, no matter if you really make the analysis with the 2 loops and the angle, or you make this image correlation analysis This gives exactly the same data. And therefore now the goal is to make really to see nice objects with the double helix and to do SOPHY with this. Actually, Peter De Decker and Jörg Enderlein's group are working on this, and I expect that there will be nice results rather soon. Okay, with this, I want to basically finish, but not before bringing here one of my most important messages in the end of my talks, because what I realized in the last years is really that it's very important when you do all these nice visualization things, be aware what you see and what you not see, and talk to each other, talk to people also from electron and, for example, from force microscopies, and just do this so that you see maybe where maybe you look at different aspects of the same objects in different ways. And I think by combining this, you gain much more information than with single techniques. And this is also a way we go at the moment. So in the end, I want to thank, of course, all my collaboration partners and discussion partners. With this, what I talked about, I want to say especially Jörg Enderlein for this SOPHY approach, also Peter De Decker, by the way, which I just forgot here, sorry, Peter. Then Alexander Jesacher for helping us with the original approaches, and this was done also in cooperation with Andreas Zumbusch in Konstanz. I thank all the funding agencies, and of course I want to thank all my bright group members. Some of them I think are also watching now. It is not possible with fantastic people to make these things, and we really had a lot of nice results in the last years, and this is due to all of you. And thank you, of course, for giving me the chance to present this all in the webinar and for listening to this. Thanks.